So this is joint. I'm going to talk about joint work with Shobhoshachi Chatterjee. He's now faculty at IIT in Delhi. Sri Artstein from the Weizmann Institute, mathematician, probabilist, control systems, and dynamical systems. Giacomo Po. I mean, interestingly, there's a good UCLA component to this work. Giacomo and Nasser used to be at UCLA. And Xiaohan Zhang is an ex-student, does machine learning now. So he's very happy about that. Okay, so outline of my talk, I'll set some context, and that will also lead to some advertisement of other work. And that'll be these two gentlemen involved there, current student, ex-student. And then I'll talk about the main ideas of the basic idea of how we go about averaging singularly perturbed dynamics. Then how we coarse grain dislocation dynamics simulations in time in single boxes, and then how we couple it to a more PDE theory, which will show up in the context. Okay, so that is the plan. All right, so what kind of problems do we want to solve? Okay, so a couple of them. So these are some experiments, and you have ceramic micropillars, and there's a metallic thin film here. And it turns out that, so here on the x-axis, these are log of the thickness of the film. This is the compressor. So you're doing displacement control, and you monitor the load, nominal stress you plot, okay? Log of nominal stress versus log of the film thickness. Ceramic pillars, nothing else changes, just the orientation. 90 degrees to the loading axis, 45 degrees before when it was intact, and you can see what happened. So drastically, okay, and the result is, okay, so the shearing off looks, that's the dramatic thing, but look at these results here. So the experiment for the as deposited film in the ceramic pillar, in this orientation, the log stress versus log of thickness, the scaling is 1, so -1, okay, the exponent. In the 45-degree orientation, material remains the same, nothing changes. You're doing the same experiment, just the orientation change. There's almost no effect, okay? It's 0.2 minus 0.2. Go figure, explain this, yeah? Why should this happen? And look, I mean, and everything that I'll show is very, okay, so there'll be crystal, actually, you could do this with J2 in the thin film, wouldn't matter. Very minimalistic, okay? So I'll show you a PDE framework. Anything I'll show you is not because something is fitted. There's nothing much that is fitted. It's because the theory delivers certain features. Okay, and also, and these are predictions of strain gradient plasticity theories. For both cases, so the compression, it gets it right, 1, but the shear also, it does exactly the same thing. And what it has to do eventually has to do with the boundary condition of the theory, okay? If you don't get the boundary conditions right, I mean, and that's structural. I mean, that's structural meaning structure of the theory itself. There's nothing you can do. You can fiddle around with constitutive equations, whatever, won't do it. Okay? So that's one example. Second example is, I don't know if Irene is here or not, but very nice experiments on, these are additively manufactured nanolaminates. Okay? And so there are copper niobium layers here, all right? And again, what you're doing is, here you're doing compression tests, and it turns out that if your nanolayer thickness is 500 nanometers, so actually 300 nanometers and above, you compress it, pretty homogeneous deformation, maybe a little bit of barreling over here, right? The nanolayer thickness goes down to 30 nanometers, and you see these kink bands appear. Very localized deformation, yeah? Predict that. And these are close-ups, so this is the kink band. You see at 30% strain, So it was being compressed. And so a kink band is essentially, it's like if you have layering, some sort of layering, and deformation localizes transverse to the layering, you call it a kink band. If it localizes along layers, or if there are no layers but along the shear direction, that's called a shear band. Okay? So these are these are a few things you want to predict, and you can see the size scales. So those are the questions, right? So the kind of model I'm going to talk about, so I'm a believer in PDE, okay, no problem. And weak solutions of PDEs are very, very good, very weak. They don't allow you to do just about anything. There are some constraints, and then it works. I mean, okay, I'm a believer. And I'll show you some stuff, and you can judge from that. So briefly, very briefly, there's a model, and so this is balance of mass. Eulerian stuff will appear on this side. This is balance of linear momentum. You write it in Eulerian form. And the difference between elasticity and here, what's going to happen is in elasticity, the deformation gradient, as you know, we'll work with the inverse deformation gradient, okay? Not the deformation gradient, but the inverse elastic distortion. There are good reasons. When you do plasticity, you don't want to involve a reference. There are very good reasons for doing this. Because there is no distinguished reference, and you can't observe things other than what's available to you. So this is the inverse elastic distortion. Difference between elasticity and this is that the inverse elastic distortion has a non-zero curl. It's not a gradient anymore. And what it is called the dislocation density. So if it's a curl, then div alpha, of course, has to be 0. And the evolution equation for alpha is not something you kind of make up, whatever, but it's because it's defined as locally as a curl, so you can kind of rationalize this. This carries a Burger's vector charge. If alpha were to be localized in a tube, this would carry a topological charge because of its definition. And then the evolution equation is simply that you do Reynolds transport on an area patch. So these are line-like objects, not point-like objects. So you basically take any area patch that's going to deform, just like we take a volume that deforms in continuum mechanics, threaded by lines, and each of them carry a Burger's vector charge, so you do the bookkeeping for how much Burger's vector is contained in an area patch. Rate of change of that is whatever's coming in minus whatever's going out because of the motion of dislocation lines, and that's essentially this statement. It becomes fancy, you got to do the kinematics, right? But that's that, okay? And because alpha is divergence free, in the Eulerian form, it looks just this, right? The spatial time derivative is curl of alpha cross. This is the material velocity, and this is the relative velocity of dislocations with respect to the material. So this looks, for those of you who've stared at the vorticity equation, this looks very much like vorticity, except this is 3 by 3, a matrix. And dislocations move relative to the material. So this is this capital V. Yeah. If capital V was 0, then also dislocations can move along just like vortices, but there is no dissipation then. That's the elastic theory of dislocation. Okay. So that's that. And a consequence of this in this model is this Burger's vector conservation. Is that if you localize this and look at an equation for W, it will come out this way. This is by the way, this is the flux of dislocations. And you sort of just manipulate this. And the additive strain rate decomposition is not an assumption here. You don't have to say multiplicative, additive, and play with that. Burger's vector conservation tells you it is just this. There's no, so this is the elastic strain rate, this is the plastic strain rate, the total guy is this, all right? It just falls out. Okay, that is the PDE structure. Keep this in mind. Well, sure, keep this in mind, but that's what we'll play with. And so very quickly, some results here. I need to speed up here. This is the advertisement part, right? So, okay, so you compute. So this is a fully nonlinear theory, okay? So now one thing you want to do is calculate nonlinear elastic fields for dislocations. So here it is, and then you compare. Everyone will tell you, no, outside the core, nothing matters. I mean, it's a linear elastic field is good enough. Well, depends on your definition of good enough. Here, up to 25 Burgers vector from the core, there are 10% differences in the energy for a Savannah-Kirchhoff material. Okay? And if you look at the edge dislocation and the shear stress field, sure, the comparison between linear theory and nonlinear theory along the x-axis, which is everything everyone will show you, that's actually zero, no error. But along these diagonals, up to 120 Burgers vector from the core, there are 10% differences. And if your dislocations depend upon stress, this is something to think about. And then you ask, okay, what is the strength of the Burgers vector at which the linear theory and the nonlinear theory match? So B over 50, which is expected, I mean, in the energy, okay? And then there are, these are like, if you are, this is a problem where you take a pre-stressed sheet and you launch a dislocation in the, and it moves, so depending upon the energy available because of pre-stressing, you can go faster than the shear wave speed, so then you're supposed to see Mach cones, you do. These are calculations. And actually, in MD, this is a science or a nature paper. Gumshan Gao did, because the linear elastic theory dynamics, it breaks down very badly when you approach sonic speeds. So they did this calculation of this pre-stressed sheet with a notch. They launched a dislocation by banging one side, and then because of the pre-stressing, they saw how fast this thing goes. And their MD results, so as you go subsonic, then you have a transonic range, and then depending upon the amount of pre-stress straining that you're doing, you can go above the dilatational wave speed too, because there's an energy reservoir available. If you didn't pre-stress, this is very hard to do. It's probably not going to happen. And our calculations, in a very simplified version of the whole business that I showed you, without fitting anything. I mean, we didn't even try to fit. That was not the point. Qualitatively, you do pick up the right sort of transitions. Okay, so those are things we can do. And then, okay, so fluctuations, and you don't have to go looking for connections through post-processing to links with fluid dynamics and turbulence here. So this is, so I'll call this, so suppose you forget the relative velocity of the dislocations with respect to the material, just keep the material velocity, that little v guy, and then this, okay, this is ideal magnetohydrodynamics. So what is that? That's incompressible Euler, magnetic field, and in Ohm's law, basically, for a perfectly conducting fluid, okay? So these are Maxwell, this is Euler pressure driven by the magnetic field. If you make the right, okay, so in dislocation dynamics, if you say, no, there are no shear stresses this thing is generating, so this is a solid not generating stress, that's not how it goes. But let's say we drop that, we drop the mobility of the dislocation. So the dislocation only moves with the material. Alpha is a 3×3, B is a vector field, but look, it's exactly so here there's some coupling between the magnetic field and the dislocation density is 3×3, so this has to become a vector. This is how it does, but it's exactly the same thing, okay? So you could say, yes?
So B is just a regular
matrix.
Oh, B is a matrix.
No, B is a vector field.
Yeah,
Sorry, B is a vector.
And alpha is a matrix.
Alpha is a matrix, so that's why I said this is a 3×3, R3. And, but the only difference is, here there is some coupling between the rows of alpha, but otherwise exactly same structure. So sure, you'd expect things like turbulence here, and we've dropped the material velocity. So now if you had the material velocity depending on the stress, which it does, there'll be even more fluctuations in the velocity field, okay? So that's that. I don't have the time to get into this particular slide here. This is a recent paper by Farako, Lindbergh, Sakehide. These people are really making, in my mind at least, and I think it is true what I'm going to say is, they're really making advances in turbulence, okay? I mean, so questions like, can you preserve magnetic helicity with energy dissipation in incompressible Euler? And yes, it does. And you know, okay, so there are questions of, well, I mean, they do dissipative solutions, so that's fine. So there are things like that that can be said, and these I would expect them to be, because of what I showed you in the structure, this would go. So in some sense, the dislocation mechanics model is you know, this stuff is contained in that in some sense. Okay, so this is the PDE structure we are talking about.
Can I
Yes?
go back to your equations there? So, okay, so basically in dislocation dynamics, all those are densities, right?
Yeah.
They could be line singularities and all that stuff's contained in there.
Yeah. So just like vortices in Euler.
In the weak form, you can
Yeah.
everything.
Yeah.
So, are you saying somebody has an MHD code could convert it to do?
Yeah, I mean, so this is ideal MHD. You've left out the viscosity, and there are questions of ideal limits, etc., which I don't. Yeah, absolute. That is the point I'm trying to make here. And this is a mathematician's. You know, it's not exactly the same, so there will be new results too. But this will be fantastic on this side too. But yes, there's some nonlinear coupling here between the rows of the beam. Think if B was a matrix field, so then that. But apart from that, it's pretty much exactly the same.
Just scalar elliptic equation vectorial look exactly the same, and they're not at all.
Say that again.
Scalar and vectorial elliptic equations look the same, but they're really not the same.
Yeah, of course. It will be, yeah, but understand one thing on the velocity, and these rows are uncoupled. So it's truly only over here. And I wouldn't expect that this thing will not show the features that's in here. If anything. But yeah, sure, your point is well taken. Okay, so see, I mean, until now what I've told you about is a model at very fine scales. In some sense, you are resolving every dislocation. That's the thought you have. Of course, for doing the test problems that I showed you, the experimental problems, you want to be able to say something at the mesoscale. I mean, just saying I'm at the scale where every dislocation is resolved is not going to cut it. And then you have to have some notion of averaging. This is for mesoscopic plasticity and macroscopic. This is the real question. And there, of course, then I'll show you. So you can take those equations, just like if you would do for weak limits, you average them with respect to test functions. So you can think of this as a test function. This is so W as a test function, which has compact support here. But the idea is you start to write averages. You averages with some filters. And the weak limit idea, as I understand it, is simply that it's for a whole class of filters. I mean, there's no scale you impose in the weak limit situation. So you can think of it that way. And when you do that in this sort of a situation, under some assumption, so basically there was a curl of alpha cross V. You have to average that in the microscopic theory. Most of the times, sort of the compensated compactness magic is not going to happen. Here, you can even explain physically why the average of the products will not be the average, cannot be the product of the averages. So a piece is going to come out, which is the difference between the mean of the product of two terms minus the average product of the averages. And this is what engineers actually feed in with constitutive assumptions, and for good reason. This is hard. I mean, as you can see from the structure. So that's, and so what I'll show you a couple of slides is that you make for here. So when you have something that you cannot fill in, we make the simplest possible assumptions on that, not get fancy on this. Okay, then there is enough phenomenology developed about this. So we put that in, but there is still enough structure. For example, okay, so I talked about the nanolaminate business, right? Okay, so microstructure, I mean, for the micropillar compression, 45 degree, 90 degree, the experiment was 45 degrees, 0.2 was the exponent, 90 degree was 1. Our results are, in the 45 degrees, what happens is, we don't allow cracking here, so this thing kind of folds over and self-contacts, so we stop the calculation there. And so it gets down to 0.395. If you do the freestanding shearing of a film, it's 0.1, so that's good. And micropillar 90 degree compression, ours is for the pillar, it's 1, exponent is 1. Okay? And yesterday we heard the talk, Jaime's talk, about fluctuations and stress strain curves, etc. This model, the one I just showed you, with the constitutive equation put in for LP, completely plain vanilla. It has been going on for 60 years now. Nothing fancy there. There, you get that. Okay. And for the micropillar, for the nanolaminates, again, we do a minimal model, right? So it's copper, niobium, BCC, FCC. We just said, okay, let's see whether, the essential features can happen in a simple situation. So it's a planar model, just 3 slip systems in both materials. And you saw the kink band. There's the kink band. We can also get the other orientation. We understand that. But we get the kink band. Okay, this is the strain profiles. This is the dislocation density profiles. And when you make the layer thickness larger, then you didn't get anything. Yeah, that's what happens in our calculation. Okay, forget this bump. That's refinement related, but we can do a calculation better. Okay. Just that. All right. God, this is bad. Okay, so now I come to the advertisement is over. Now the real stuff, right? Okay. Well, that's real too. So I want to be able to talk about, we want to be fundamentally, okay, even in the dislocation context, the question I want to ask is, so we want to fill in constitutive equations for that LP from microscopic stuff. So here we'll assume discrete dislocation dynamics will be the microscopic model. So what can you do? And there are huge differences in time scale. You pull these things at 10 to the minus 3.001 per second, okay? So 1,000 seconds is the time scale, so to say, of the loading. And free flight of dislocations, you're going at nanoseconds, tenths of nanoseconds, hundreds of nanoseconds, okay? Free flight. And then these things get stuck, then they'll go. So what are you going to do? So time averaging is an issue. So we thought of thinking about that in the context of ODEs to begin with. Hard enough as it is. So think of ODE systems of this form. This is what. So you see, dx by dt, there's a 1 epsilon is a ratio of the fast time scale to the slow time scale. Okay. If it helps you, I think a clean system, rather than think dislocations, you're going to think of a bunch of atoms in a box. You're going to load it. You're loading it very slowly, and this thing vibrates. All these atoms vibrate, they're going to do something. So you have the atomic coordinates and the velocities. You have equation, Newton's laws. And here, as written over here, you see this is not a split into slow and fast. This is the loading. The loading is evolving in a certain way. This is not a split into slow and fast variables. You can't do that. So you don't have that a priori split. Okay, what can you say about this as epsilon goes to 0? Meaning I want to look at that limit. Okay. So when you have such systems, the characteristic behavior is this. Two cases really lay out what the possibilities here, at least as I see it. One is if you can have a system where, okay, so they all kind of look similar, but see this particular guy, if you set it to 0, it will be this manifold over here. There's an unstable branch, these two stable branches, okay? So I didn't plot the unstable branch because that's not where the dynamics goes. Okay, so you put any arbitrary initial condition. Suppose I put this, it'll very quick, so this guy equals 0 will be that manifold. That's a slow manifold. If you put any initial condition here, the y will very quickly, in a sort of a initial layer, it'll come down here, close to this manifold, then y will go slowly along, and x is moving slowly here. Look at the rates. So there's a 1 over epsilon here. So, but y does become slow when it comes here because this is very close to 0 also. So this is small, slow. And then over here, it doesn't go that way. Yes, sir, it makes a very sudden jump. Say that again? This is maybe, I'm not sure, but some variant, if not, but very close. Okay, it makes a jump, then it'll go back, jump, so you get this kind of profile, right? So what this is so one particular type of system is when the slow variable, for fixed slow variable, the fast guy comes down to a particular fixed point in phase space, all right? So in that case here, you can say that the fast dynamics is slave to the slow variable, meaning there's a manifold, there is one, so you might be able to parameterize the slow dynamics on that manifold, and if you could achieve all that, then you're good. However, life doesn't work out that way. And I'll give you explicit examples and I'll show you calculations, right? So typically, what you'd expect, the typical behavior is going to be this. So you do the same thing, and we just mucked around with this, and this is modified to adjust these equations. So now you have a few more, and you start from there. This comes here. What it comes down to, however, is it keeps whizzing around. There is still fast dynamics. So essentially, you don't have a manifold. What you have is at most a bunch of invariant measures for fixed slow variable. By invariant measure here, I just mean that, think that dynamics came down and it's going for, if you just kept letting it go, okay, for fixed slow variables, it's going to track out a set of points. Everyone who does MD knows this much better than me. This is the usual calculation, statistical mechanics type, right? So you just let one trajectory go, it's tracing out stuff, and the points I'm drawing, think of that as a support of the trajectory as it's going around, yeah? So it comes down, and it keeps whizzing around like that, but it slowly drifts. Instead of this manner, the measure drifts along this, and then the whole measure could sometimes jump, go back, and keep doing this, okay? Once this happens, so clearly there is no, while it looks like, you can't do adiabatic approximations just like that. You can't just hack out an epsilon and say, I have what I have. Mathematicians understand this very well, much better than I do. This is the idea of singular perturbations. So when you can do that, elimination set epsilon to 0, and just live with that, that's called the Tikhonov, that's a proof, Tikhonov proved this. That's the Tikhonov approximation. You get DAEs, but not in general. This is what's going to happen, okay? So no slow manifold, no slaving, fast remains fast. The convergence result is, so here's a bunch of stuff, and I didn't mention Wassow, Verhulst. I mean, there are some Bogolyubov and Mitropolsky, so there's some classic stuff. That's like Bogolyubov and Mitropolsky for me is like Newton. You don't mention it. People who do MD don't say Newton reference. So that's the kind. But that's that. There's a very nice paper by Friedrich Mitch, and I don't know this gentleman, but so I enjoyed that paper. It's nice. So you have Nose-Hoover thermostat is not actually ergodic. So ergodicity. So I should have made this point. So clearly, everything that we are talking about, no ergodicity, right? I mean, for fixed slow variables, I start from initial conditions. Here it goes to a completely different invariant measure than this guy. So go figure. All right. So that's a bunch of references here, and it does include the HMM and Kevrakidis' equation-free business, but okay, all of this doesn't do this business, that as epsilon goes to 0, it doesn't tell you a practical scheme for generating slow variables. The best results in those things is, suppose you had a slow variable, and orthogonal variables are slow in a certain sense. Orthogonal meaning, that f, 1 over epsilon f that appeared, you take a phase function whose gradient is orthogonal to that f, that you would call an slow variable. Then you can pass to the limit as epsilon goes to 0. But who's going to deliver these phase functions? No one is going to, you don't know what those orthogonal variables have to be. And even when they are there, if you, and I've looked through this carefully, there is not a good recipe to figure out how you're going to initialize calculations after making long time step jumps. Okay. Very good. So what's our take on this? So I'll keep it simple. No math here. I mean, just some very sort of by hand you can understand. I'm going to try to spell it out that way. The first thing is, what are good stable coarse variables, right? So a good stable, okay, so first the convergence result is Artstein and Vygodner is really the 1996 proceedings of the Royal Society of Edinburgh. I used to fiddle around with these time average things, and then I saw this, and this is really a tremendous paper. So what the main result is that for the slow variable is characterized, the slow dynamics is characterized by a Young measure. What a Young measure is, just think of it this way, you want to, on the slow time interval, you have a slow time interval. For every time, you have a probability density distribution in phase space, in state space, okay? So velocity, whatever, there's a fine dynamics, there exists under very minimal assumptions of boundedness essentially on the fine dynamics. You have a Young measure on this guy. That's what characterizes the slow dynamics, and then observables will be something that you can average against the Young measure, but that still doesn't give you a rule to evolve such observables. But the idea to keep in mind is that theory says that take the ODE, as epsilon goes to 0, the limit dynamics is characterized by this Young measure, okay? On the slow time interval. So here's the first big, our contribution. On-demand coarse variables, right? So the goals are very modest, okay? I am not trying to say that you know every little thing that the dynamical system is doing, we are going to characterize. This is what the mathematician will do. I give you ODEs, and I give you initial condition, characterize the entire dynamics. No. This is far more modest, okay? All you're saying is, I'm going to take some averaged coarse variables in time, and the averaging, this is how it is, okay? So there's some history you're building into the coarse variables itself. So I told you that for every slow time, there is a Young measure, right? That's the mu s, and x is the state space. So mu s is on dx, so this is the probability density on the state space. And you take any phase function. You take your pick, whatever you want to make out of the thing, right? Any phase function m, you integrate it with respect to the Young measure. So that's on the whole state space. Of course, this is not practical. We'll find a good practical way of doing that. And after that, you integrate it in time for a little bit on the slow time, okay? And this is a model variable. You're saying on slow time, I'm averaging over these kinds of time scales. And any such observable that you can set up corresponding to a choice of m is guaranteed to be slow. You've averaged it seriously. That's a theorem, okay? And how are you going to calculate these guys? So of course, if I say figure out an invariant measure, then average, of course, go home. No one is going to be able to do that. But the invariant measure comes out, the Young measure comes out, the values of the Young measure by occupational measures, meaning the regular stuff that we do. You start from some initial condition, fix the loads at that time, and then you run it, and you take the value of m and you average it along the trajectory. And okay, then you do the horse trading. At some point you say this is done. So I'm going to now stop. I have the limits. Okay, so I'm going to, for every m, I'm going to define as something called an Rm of s, okay? Then this, if this is your definition of the coarse variable, you just do a rate of this. This is just Leibniz, really. So you see, this fellow is the practical way of calculating this is by time averaging along a trajectory. So you calculate this guy at time t, you calculate this as t minus delta, 1 over delta remains outside. The evolution is of such a coarse variable is this type. And now this is a huge class, okay? And then you just extrapolate like so. There are going to be savings depending on the jump you're going to do with h and even on the deltas. And so then the next question is, okay, so I was here, I've gotten up to here, let's say, then I make a big jump, my v is over here, how am I going to initiate? Now I have to move from here to somewhere else, right? How am I going to initiate this particular measure? How do I know where to? Because here, like I said, there's no ergodicity. So your measure depends on initial conditions. So you have to get good initial conditions. Yes?
If we refine this delta to the, what is the time scale it can recast all of the fine scale dynamics?
No, but you don't want to do that. That's a bad idea, right? Yeah. Because then you do the fast dynamics. I mean, no, this stuff is working only. You can do those limits only because you have a large separation of time scales, right? Epsilon has to go to 0. Otherwise, if it is mixed, then you have to solve the real thing. I mean, there's no, and even here, there will be jumps like I showed you, right? So the measure itself can jump somewhere else. So. Okay, so this is a coarse variable, and the next thing is how do you initialize these kinds of dynamics? And that statement is like so. So take some fixed point in state space. So it's fixed in time, right? On intervals where your measure is moving slowly, see, stuff is going on very fast on the measure, right? But you can think that the support is moving slowly. That happens in these sorts of things. Right? The Young measure is actually continuous in time over significant periods. So, okay, so this is just a fact. So suppose you take a fixed point, your measure is moving slowly. If I take a closest point projection of this point on the measure, the support of the measure as it is moving, then whatever that object is, that closest point projection is going to move slowly also. So that's a good stable coarse variable as long as the measure is moving slowly. That's the idea. So this is exactly what we do, okay? And what you do is you take something, say, okay, at this measure, you take a point on the measure, on the support itself. I'll go with support and measure interchangeably, okay? So you take a point, so that's all, the closest point projection is that guy on this measure. You had somewhere at a previous time which you had completed, you keep one state, you start running it from there, take the closest point projection of the point there, you'll get this, but this is guaranteed to be slow, so you extrapolate, you get an initial guess on the other guy. And you can do this a few different times to generate few different initial guesses for the putative measure at t plus delta t, then you generate and you keep going. Yes, Hannah? No, delta is a model parameter. I'm saying this is why I said my goals are modest. I am not, so for example, I don't think this thing will get you a single rare event. Okay, but if there are many things that are happening over the delta time scale, that's what is making it work. This is why you can have like on-demand coarse variables like this. And I'm interested in such things. I gave you example, 10 to the minus 3 per second, okay? That's what I want to load a MD box at.
So you're saying you're choosing the delta to whatever time scale you're interested in?
Yes, more or less. It's.
You think some effect's going to happen in this time scale, so that's what you're doing.
Yeah, exactly. This is going to be slightly less than the loading time scale because you want to refine that, but more or less exactly that. But that's exactly the kind of thing I'm interested in, being able to talk about.
Can I ask?
Yes.
So, I mean, theoretically, if I understood correctly, this M is an observable. So you can still choose whatever M you want.
Yes.
So that still doesn't really answer what is a good M, right?
No. Actually, you take that off the table. Okay. The question has been changed. I've created these kinds of V's. I mean, and that's what I want to do because you know as well as I do, finding constants of fast motion is not easy, right? there aren't too many good m's around. Okay, so that's the game, and very good. Okay, so you remember that example that I set up? It's basically, if you run the fine guy, so y versus x, you see the y versus x profile is going to be this fellow. And the z versus w, w is also on the x-axis. So the w is doing that, and z is going around like that. And then once in a while, it flips up. So you see, the measure itself jumps. Meaning, even the slow dynamics is not really slow at all times. It can go. And this has, it can jump. That's just what it is, right? So if you look at the averages over here, so the z versus w, that's doing this, okay? And the y versus x is doing this. And this compares very well. I mean, because we can run the fine dynamics. We just brute force work this out, yeah? And these are some pictures of what these fellows do. And another thing I should tell you, so how does it handle the jumps, our business? I mean, how does it do this, given that extrapolation rule? You see, what happens is, as you're moving along over here, going from measure to measure, so at some point you'll extrapolate the jump guess, this is an exact guy, jump calculation comes here. But if the measure itself jumps, this thing is in the basin of attraction of the lower measure, no longer up there, right? So you put it there, it just goes up there, and then it'll whir around there. And this already starts to tell, this I find fascinating, right? So suppose now, in this region, now let's say there were a whole bunch of measures whose basin of attraction is very intermixed. So it's a completely deterministic, presumably one could cook up something like that. It'd be fantastic, right? So suppose it's very intermixed, then you could, depending on what, like, you know, this guy, if there's a little change, you can go to some other measure, otherwise you go here. It automatically almost spawns like a stochastic. I mean, already there is this statistical kind of thing, you're averaging, but that would be like, you know, you go into different basins and each one of them can take off in different ways. But that's that, and we have good savings, okay? So epsilon going to 0, 10 to the power 3, even in a four atoms, not 4 atom, but 4 degree of freedom system as epsilon goes to 0, okay? And so I won't get to my dislocation application part maybe, but that's all right. I want to get this guy across, and you know what applications we want to do. We've actually done that. It's published. So now look at this. This is as simple as it gets, right? Everything is linear here. Linear dashpot, linear springs, connected. That end is fixed. I'm going to pull this guy slowly, yeah? Question. There's a big dashpot sitting there, right? Do you expect oscillations to persist? I don't have too much time. Answer, at least if you asked me before thinking, I'd say no. If I'm an engineer, come on. I mean, there's a linear dashpot sitting there, what? But you can kind of, if you think about it for a minute, you see what's going to happen. Maybe more than a minute. If you have a free vibration mode that moves this rigidly, then you're good, right? So then the dashpot is seeing nothing, and you're going to oscillations persist. And it turns out that if you have K1 over M1 is equal to K2 over M2, then you hit that. If K1 over M1, the mass, K is the spring stiffness, right, is not equal to K2 over M2, then that mode will not be in your free vibration spectrum. But otherwise, it will be. But when K1 over M1 is equal to K1 over K2 over M2, you know, for all initial conditions, almost all initial conditions, except in one hyperplane in state space, you are going to have oscillations persist. So it's not like some measure 0 kind of, okay, if you put K1 over M1, all that parameter space 2, then it's measure 0, but not otherwise. And our scheme picks this up blindly, okay? You set K1 on, you just do what I said. And And when K1 over M1 is not equal to K2 over M2, you get the Tikhonov result. You hold it and it goes to 0. This is the DA business, picks it up. When you have K1 over M1, the equality thing, kinetic energy is preserved. You have equipartition UF. Errors are very small. Things go well. And we always find that whenever you have some dissipation and like the system, actually the invariant measures are supported on Dirac, so on points, then things go very fast. You get big time step improvements. Like over here, you see epsilon 0. These are really small systems, but you get speed ups of thousands. Whereas when you have oscillations, slow oscillations, fast oscillations, and then there's a drift, that's significant. I mean, the speed up is not that much, but still quite a lot. 45, okay. So this was all, this is an ODE setting. I hope to have conveyed some idea of what the overall scheme is over here. Then what we did was, of course, we got money from NSF to do this too. Write a proposal. You don't understand what you're going to face. This is the nature of a proposal. DD was the worst possible thing we could have chosen as the microscopic system. And I'll tell you why. Because, DD is, like, there's a lot of stuff going on there, right? And you change, the basic problem was our state space doesn't remain fixed in the DD way of calculating things because number of segments are changing. So this business of what I feel the best about, this whole closest point projection out the window. What closest point projection? The number of things don't even remain the same. If you had a PDE model downstairs and working really well, then maybe you'd be able to pull it off, but not with DD. Anyway, DD was the choice. So Giacomo scored UCLA things, stuff that happened here. That's that. You can generate, so I'll do this quickly, okay? So you can, rho is our standard, the line length per unit volume measure. So that's it works out in terms of microscopic stuff. This is another guy, this is the velocity, plastic strain rate, alpha cross V bar. You can define all of these in terms of the discrete dislocation configurations, okay? And one thing we had to resolve, and this was another thing with DD, right? And here is something where microscopic stuff can really help. So if you take a box and you see free flight of dislocations, you do a little calculation, 1 micron cube box, the strain rate will come out to be 10 to the power 11 per second, free flight, okay? You average that over the whole box, meaning, plastic strain rate is happening only along the segments. You average it on 1 micron cube. Come down to 10 to the power 3 per second. This is also not slow enough. This is not 10 to the minus 3 per second, okay? All right, very good. So now what can you do? So then you say, okay, but then the junctions will form. But this is what happens. See, junction breaking is not a part of DD as such. So junctions means, there are dislocation lines, you go there, there are rules and they get stuck, okay? But once it gets, by what do I mean by junction break? This is thermal activation, right? So at low enough stresses, like 20 MPa, 30 MPa, a single crystal of copper will go yield at 17 MPa, let's say, MPa. You put 17 MPa on a DD or anything on a MD box, nothing is going to happen. Okay, so junctions have to form to get this small, but then, without junction formation, you have a very high strain rate. But if you form junctions and you do nothing else, strain rate will be 0 for the stresses that you want to see something at. So what are you going to do? The issue is that what happens in reality? In reality, there's thermal activation, so dislocations can actually move past these obstacles, right? This is not part of the microscopic model we are talking about. So we made a model. Once you understand that business is going on, so you say, you're going to draw this randomly in 0 to 1, and then there is a breaking time, which is 10 to the minus 3 per second, and junctions break like this, right? So as I said, once you get into this, it's like tremendous horse trading going on. You just do what you have to do. But this is realistic. So someone has to put in this input into D to be able to do something at realistic stresses. Once we put this in, then we started to get average plastic strain rates of 10 to the minus 2 per second. Okay, this is now you're talking. So 49, very good. That's all in there. So we set up a double slip configuration, uniaxial tension, double slip. Okay, so and then you do stuff and you're loading it at 2. This is load control 2 MPa per second loads and stress strain curves. This is a no constitutive equations. Everything is just inside DD, right? You're just averaging by this scheme. You know, and when you do this, you realize that the stress is not obligated to even go in the right. Plastic strain may be happening this direction. You're doing all this averaging. Stuff might be going in the other direction. Stress could be going negative too. So even this is in some sense a prediction, okay? You go up to 10% strain. You shouldn't go up to 10% strain with a small strain DD theory, but that's a separate issue. These are stress strain curves. The hardening modulus, you know, experimentally it's known that you get up to shear modulus by 200, the hardening modulus. It does come down to that. So, and then we coupled, remember the PDE model that I was talking about? So there it required an input for the LP guy. So the idea is now this is that LP, this is going to be fed in. So at the macroscopic scale, it will be the PDE. And so the idea is at some element Gauss points. So let's say you think that there's a 1 micron cube box sitting there. This guy communicates with the loads, sends in a stress, and then this box sends out the time averaged LP and V. Yeah, you're fitting nothing here, right? And then so you average stress over all Gauss points in a block. The stress comes from the macroscopic calculation. Apply this ODE technique to get LP and V. Interestingly, just at this plain vanilla level, you can't say something. Typically, we prescribe constitutive equation for plastic strain rate. Here, what you are prescribing a constitutive equation for at the element point is the rate of plastic strain rate. This is all you can do because plastic strain rate is specified by the state. Use those two to do the PDE problem to get the stresses equilibrated, etc. At the macroscopic level, go back, keep doing this. 5 minutes, right? Yeah. So we have that scheme set up here. We can do calculations. You know, you get sort of in terms of speed ups. You can do calculation. This is like out of the world, huge, obviously, because you can't run DD for even a single jump. So if you can do something, and I don't have the time. There actually does, even this plain vanilla, very crude sort of thing, first shot, does quite well. Well, I shouldn't say first shot. I mean, Sabyasachi's thesis was this. So the two pieces that I've talked about. So, and there are, you can plot things. And I want to end with something that thrilled my soul was, so I want to show you one result, right? And then I'll end. Focus on this black. So these are for different sessile and mobile density. So we say some dislocations are simply sessile, mean they're not moving. They're just planted there. They create internal stress, and there's a, but those densities are high. We are not talking like Mickey Mouse things here, okay? 10 to the 12, 10 to the 15. I mean, realistic stuff we put in. And we are doing this at low strain rates, really low. This is all, okay, good. So I want you to focus on this curve over here, right? So this is being, somehow we find that load control goes better than displacement control in this business, which is kind of not intuitive. So yielding behavior seems to come out very easily here, no big deal. Almost everything shows some flat profiles. That's not a thing, right? But over here, look at this black guy over here. This is like there's a stage 1 piece that comes out, stage 2, and then stage 3 parabolic, right? This is an output. For those of you who know what I'm talking, I mean, these are distinguished things in a stress strain curve for, say, FCC crystal, okay? So you start loading, and then there's the elastic part, then there's a stage 1, and no hardening. And the size of that depends, and then there's a stage 2 where there's very rapid hardening, and then the hardening starts to die off, okay? And this is, mind you, nothing has been put in by hand. Everything that has been done, I've told you, yeah? So that's that. And but you know, there is still a huge dependence in the microstructure. I mean, this state, the stuff that we could not do, that closest point projection business, the coarse variables that we are working with does not give, okay, one way to summarize this is, does not give you, if you just work with this, you'll have to do many realizations and then average over those guys too, because it does not come out as something deterministic. I like deterministic stuff. So I think that's a good place to stop. Thank you very much for your attention.